Okay, once again, hello and welcome everyone to our first event of fall 2021 in the MZES Social Science Data Lab. My name is Dennis Cohen and I'm happy to welcome you to today's talk by Sarah Shugars on network models for political conversation here in the Social Science Data Lab. The Social Science Data Lab is an event series at the Mannheim Center for European Social Research, where we provide a platform for early career scholars to present tools and methods for the collection, management, analysis, and visualization of data in the social sciences. The Data Lab is organized by myself in collaboration with my colleagues Cosima Meyer and Julian Bernauer, with the support of our new student assistant, Andreas Küpfer. So our presenter here today is Sarah, who is an assistant professor at the Center for Data Science at New York University. As a computational social scientist, Sarah works on topics related to American political behavior and develops new methods in natural language processing, network analysis, and machine learning. In their talk today, Sarah will talk about network modeling choices for modeling the social, semantic, and conversational networks of political discourse across a range of different contexts. The workshop will feature some hands-on applications in Python, and you can find the workshop materials in a Dropbox, the link to which I'm copying and pasting into the chat right now. I'm also copying and pasting Sarah's instruction for installing a Python environment on your system, which you may wish to do if you want to follow along with the applied exercises on your machine here today. Before I hand over the floor to Sarah, I'd like to say a couple of words about the logistics for today's talk. You may ask your questions during the workshop or in the Q&A that follows the workshop, and you can do so in 3 different ways. You can either raise your hand in the Zoom chat and wait for us to call on you, and then unmute yourself and speak, in which case your audio and video will be recorded. Or you can post your questions in the chat or send them to me via DM, and we can then read them out for you. Remember, here's the disclaimer once again, that we're recording this live stream in active speaker mode, which means your audio and video will be recorded once you unmute yourselves and speak. So with that being said, Sarah, we're super happy to have you here today. Thanks so much for being here, and the floor is yours.
Great. Well, thank you so much for that wonderful introduction. I am going to go ahead and share my screen. Okay, and then got to get all my windows open. I feel like it's like a whole setup to get started in Zoom. Okay, so welcome to this talk. Good afternoon to you, good morning to me, perhaps good morning to some of you. I don't know exactly where everybody's located, but I assume it's afternoon for all of you. So as Dennis was saying, this will be a talk that's about thinking about modeling choices for political conversation and particularly using Python for doing that. So just as a quick outline for this workshop, I'll start by giving a talk about some network models of political discourse and sort of hopefully illustrating why this is an important question and also why it's a challenging question. And then I'll go through some code looking at modeling and analyzing these networks, particularly using Python. So this first part of the talk should be about 15 minutes or so. So that should leave us plenty of time to do the coding section and really walk through some of this code. And my understanding is that most of you have worked primarily in R, so Python might be a little bit new. So certainly, please do feel free to interrupt, ask lots of questions. So you can ask questions either about the theory on the technical side, or again, even just syntax. I was telling Dennis before this that I do use both R and Python, but often I feel like I use primarily Python. So then when I try and code in R, like my brain gets scrambled and I can't remember like the simplest things sometimes. So feel free to ask any type of question. I know when you're sort of coding in a language that's new to you, it can be confusing or discombobulating to see sort of the different syntax. And also feel free to reach out anytime in the future if you have questions either on this specific code or sort of this line of thinking, I'm more than happy to make some time to chat. So with all of that being said, the research question behind this work is really about how we should model political discourse. And this is one of those questions where, I spend a lot of time working on political discourse and thinking about political discourse, and there are sort of ways that we approach it, and it mostly works. So like, you kind of do your project and don't worry about it too much. But this is one of those things that's sort of been bubbling in the back of my brain as I've been doing a lot of other projects. And this is currently a work in progress where I'm trying to think about this question more deeply and sort of formalize some of these approaches. So there are a lot of related questions here. So thinking about like, what are we actually talking about when we talk about political discourse, or what are the elements of that? What types of things can we actually observe or measure? And also what data is available to do that measuring? And the overall goal of this project is that these modeling decisions should be intentional. So as I'm sure many of you can appreciate, there's not necessarily a like, here is one single way that all political discourse should always be modeled, but rather there's a lot of different researcher choices that can be made in doing this modeling. So thinking about exactly what those choices are, and hopefully providing some resources to help researchers make informed decisions when making those choices. So one sort of big picture computational social science challenge here is that often the data that we're working with was created for, or even just a byproduct of, some other process. So this often means that there may be a disconnect between what we want to be measuring and what we're able to measure. So Matt Sigalnik talks about this in his book, Bit by Bit, where he differentiates between custom-made data, which is generated and collected for a specific research purpose, and ready-made data, which is created for some other reason and then sort of repurposed for research. And often when we're talking about sort of measuring political discourse, we're thinking about ready-made data where we're not necessarily developing. We could develop a lab experiment where we have people come in and talk about something political, but if we're interested in sort of observing political discourse in the wild, as it were, that usually means taking data that already exists. So like social media conversations where people just happen to be recording their political discourse and then trying to repurpose that for understanding political discourse. So just as a bit more of an example of this, imagine two different approaches to sort of measuring public opinion on a topic. So sort of the traditional approach would be that we would ask a random representative sample some series of questions about their view, and we could even do lots of pre-tests to figure out exactly what the right questions are to ask, what wording to use for those questions, and essentially we would be designing and fielding a survey in order to measure public opinion. Now, the ready-made example of this would be to say, oh, people are actually freely posting their opinions on social media, such as Twitter, for example. So if we want to know what people are, if we want to know public opinion on a given topic, we can just collect a bunch of tweets where people have sort of put their public opinion or put their personal opinion out into the public sphere. And we can analyze those tweets to determine sort of what people are talking about and what public opinion looks like. And the important thing to note here is that both of these approaches have flaws. As we know, there is unfortunately, no perfect way to do science and to measure things. But one thing that's also important to note here is that this custom-made approach, so in this example, like doing a survey on public opinion, there is whole literatures of work on how to do this properly, what kinds of errors you run into. There's lots of collective knowledge about the flaws of this approach, whereas with the ready-made approach, first of all, the system keeps changing. So again, if we're thinking about Twitter data, what information is accessible through the Twitter API changes, the specific mechanisms of the Twitter API or the Twitter platform will change. So we don't necessarily know, what information is being promoted by the algorithm, and that will probably change over time. And it's also just new. So there's lots of different moving pieces, and we're sort of collectively being like, well, it kind of works, but we don't really know what the errors are. Okay, so that is all to say, the focus of this session is really on this ready-made piece and thinking about what does it mean if we use this passively collected data to try and measure public opinion or sort of how people are talking about politics or sort of something broadly in that space. So one common way that we might think about doing this is that we could take all the statements on a given topic. So again, we might collect all the tweets using certain keywords, and then we look at sort of the constituent words in each of those documents. And we consider words that co-occur to be connected to each other. And if we aggregate over all of these statements or documents or tweets, then we can create a semantic network of word co-occurrence, which captures the words that tend to be used together. So this kind of word co-occurrence approach can be very helpful, particularly in thinking about topics that are very polarized. So you might look at different communities and see that sort of one group of people is talking about an issue one way and another group is talking about an issue a different way. And there certainly are interesting things that we can glean from these kinds of semantic networks. But at the same time, it's important to note that this approach sort of comes with this underlying implicit assumption that all of those documents that we aggregated over were generated independently in a sense. And it's not necessarily a commonly articulated assumption of this approach, but I do think it's something that's important to think about. So one way we can think about this assumption is sort of through the two-step communication model that Katzenlasersfeld introduced. So we might imagine that the media covers events, or perhaps just events happen in the world, and that sort of exerts some uniform force on people who talk about things, so on opinion leaders in particular. So each of these opinion leaders then go and they tweet their hot take about whatever this thing is that's happened, and then we aggregate over those essentially independent documents and get this network. And you might, I guess part of the question here is, to what extent does it matter if we assume those documents are independent versus connected? So we might think, well, okay, technically they're not all independent. Some of them might be connected, for example, in a conversation. One empirical question we could then ask here is, how many of those documents are in a conversation with each other? But just conceptually, there's good reason to think that this kind of conversational interconnection could influence our results or our interpretation of those results. So if we collect a whole bunch of tweets, for example, and we find that almost all of those are part of a single conversation, we might also think that the replies to a topic are not totally random or totally independent statements of opinion, but they're actually moderated or mediated in some way by sort of the content that they're responding to. So that could include the specific words you use, it could include the tone you use, it could include a lot of different things that would be sort of measured in this approach. So here we see sort of two of these levels of networks that might be connected to each other, where conversation networks are sort of a connection of documents are connected to each other. Those documents are made of words, and those words make a semantic network. But then there's also a third type of network that we might be concerned about here, which is the underlying social network. So each of these statements, they're also not generated necessarily by independent authors. We could have people, first of all, you might have a person who's generating lots of statements themselves, but there's also sort of this underlying social network, where again, we might expect that social network might have impacts on what kind of data we observe or how we interpret those data. Because, if assume that you do observe a response between two people, how you respond to somebody might change based off whether you know that person or whether they're a total stranger. So again, there's sort of reason to think that sort of this social relationship that goes into this sort of discursive system might influence what this looks like. So again, we might see that like observed statements could be mediated by existing social relationships. So now we have these three levels of networks where there's sort of different things happening in each of these networks. And as you can imagine, this is a challenge because you really can't just say like, well, we'll just do this multi-level, multi-modal network. There's like too much going on here to model. So typically what researchers do, and I certainly do this as well, is we sort of focus on one of these networks and say, okay, we're going to do like, look at the semantic network for this project or look at the social network for this project. And again, the key question here is, does it matter if we do that? If we ignore sort of these other interconnected networks, is it actually going to change how we think about the results in our data? So as a sort of empirical example of this, and this is sort of the code that we'll be using, we'll also walk through a subset of this data. So I collected a corpus of about 2 million tweets that took place between April and May of this calendar year, focused on the topic of Black Lives Matter. They're all originally authored English language tweets. And so just to give you a quick sense of what this looks like, so we can see some peaks in the data. This was around the time of the murder trial for when George Floyd was murdered. And so you can see there's sort of a peak as the trial started, a dip when the weekend happened, and then another peak again, and then it sort of tapers off a little bit. So this just to give you a sort of conceptual sense of what was happening at the time. And again, thinking about that semantic model, what we might do is sort of take all of the individual tweets that make up this time series, look at hashtags in particular, tend to be, very capture a lot of the information about what a tweet is about. So we take all the hashtags in those tweets, think about if two hashtags co-occur, we consider them to be connected, we aggregate over all of those tweets, and then we create this hashtag co-occurrence network, where we can see that there are sort of different communities that form and sort of different things that people seem to be talking about in relation to the Black Lives Matter movement.
Sarah, sorry to interrupt you for a
Sure.
second. I received a question via DM,
Mm-hmm.
and it referred to the previous slide, so maybe it's been answered through this example, but the question was whether you could elaborate on the size of semantic networks.
The size?
Yeah.
Yeah, so I mean, a semantic network could be of any size. This one in particular, so it starts with 2 million tweets, and then I actually don't remember off the top of my head. So like there's hashtags that there's often more than one hashtag per tweet. So I don't remember exactly what the number of hashtags is, but sort of order of magnitude, it would be, more than 2 million, less than 10 million, probably somewhere in that range. But in principle, you could have a semantic network of any size. So there are projects where people have used semantic networks in like literary text. So you might look at, there's some fun projects where it's like, what characters appear in scenes together in Game of Thrones or something, where it's looking for, those characters' names in the script of a TV show or something. So it could be that, or it could be looking at, a whole corpus of, like every speech made before the UN over all time, and then doing that. So there's really no bounds on how big it could be. So sorry, yes, this is the slide I'm on. So again, the semantic network sort of ignores the conversation level. So some of the things that we might be concerned about in terms of interpreting this is thinking about, are some of these documents interconnected to each other? So are some of these tweets that we're seeing actually just part of the same conversation? And then we also might think about, are there interconnected documents that are missing? So we sort of used keywords that seemed relevant to our topic to identify our starting corpus. But if some of those tweets are like part of a conversation with other tweets, then do we want those other tweets to be part of our corpus, or maybe we don't, or like, what are the bounds on that? So just to give you sort of a sense of how big of a problem this might be, in this 2-month data set, so again, we have about 2 million tweets here, and about 5% of those tweets are in the same conversation as at least one other tweet. And this is, Twitter recently released an academic track to their API. So this is using that, and there's now a conversation feature where you can sort of retrieve all the tweets using a conversation ID. So overall, it's a fairly small portion of the corpus, but at the same time, there's one conversation that accounts for 600 tweets in this original tweet corpus. So again, there's not necessarily a definitive answer as to like, is this a problem? Is this not a problem? For what data sets will this be a problem? For what data sets won't it be a problem? But I do think it's telling that, we're not talking about just like, oh, every once in a while there's a dyad where there's sort of 2 tweets that are in the same conversation, but actually sort of whole conversations are being captured within this corpus, whereas other tweets are totally independent. So to sort of get a sense of how that conversational interconnection might influence our results or our interpretation of those results, we can again look at sort of the original hashtag co-occurrence network. So here's an example of the network with some of the key sort of communities discussed. And again, we'll talk about this in code in just a few minutes. And then we can create a similar network where we actually restrict our corpus to only have a single tweet from each conversation. So basically we go through the tweets, and if we see a tweet that has a conversation ID that we've already seen, we just ignore that new tweet. And what we see when we do this is there's actually sort of whole topics of discussion that seem to disappear from the single tweet per conversation version of the network. So the conversation about LGBTQIA and Pride Month, as well as sort of there was a discussion of events happening in Uganda that appeared in this original network. And it appears that those conversations or those topics were there weren't things that were being discussed by lots of people, but were sort of discussed in active conversations. So again, sort of the degree to which this is a problem might vary based off your specific corpus and your research question. But the key thing here is that without thinking about this conversational network, we can't distinguish between sort of what are issues that are widespread, that are sort of talked about by lots of people versus what are sort of specific threads or conversations that are active, but that specific topic is more isolated. So then on the other side of this, thinking about are there interconnected documents missing? So again, we start with about 2 million tweets. We can then use that conversation ID to retrieve all tweets in those conversations. And doing this retrieves about 14 million tweets that were not part of the original corpus. So that original corpus was only about 15% of this much larger conversations corpus. So the tweets that we're looking at based off these specific keywords are really only a small portion of all the discourse, certainly all the discourse that's going on, but even all the discourse that's happening in those conversations. So again, we can do a similar thing where we sort of look at our original hashtag co-occurrence network, and then we compare it to a hashtag co-occurrence network generated from this much larger corpus. And here we see sort of a similar thing, but happening in reverse, where now there are whole new topics of conversation that didn't appear within our original corpus, but which sort of seem to be things that are being talked about within this larger conversational corpus. So looking at this can give us a sense, just from looking at the hashtag co-occurrence network, we don't really know what the relationship is between those topics, but it could be that these were events that were co-occurring at the time, and people who were talking about Black Lives Matter were trying to sort of use those other popular topics to focus on their topic, or it could be the other way around, where Black Lives Matter was sort of particularly salient topic at the time, and people who were sort of interested in other topics were trying to garner attention by sort of connecting themselves to this larger discourse, or perhaps people were just like seeing natural connections between them. There's sort of lots of different questions that you could then ask just by seeing sort of the new topics that are connected conversationally to our topic of interest. So then the last piece here, which I'll just go through quickly, is thinking about the social network here, which is challenging to retrieve through Twitter. So we just retrieve a sample of those users. And here we see that only about 13% of the tweets produced by those users are part of a conversation. So most of the tweets that we see in general are independent and not part of a conversation. But one other thing that's interesting is that many of these conversations, they do, like if somebody is having a conversation, they are likely to have a conversation with somebody who they are either following or a follower of. But at the same time, only about 2% of people's social connections seem to be engaged in conversation. So again, this is sort of very anecdotal. This is a specific corpus at a very specific point in time. So I wouldn't, say this as a general rule about Twitter. But I do think it raises some interesting questions about sort of what role this conversational back and forth plays, as well as thinking about potential issues like subtweeting. So maybe I see people posting about something and I don't actually engage them in conversation, but I choose specific words or messaging for my tweets based off what I see from my social connections. So again, all of this is very anecdotal, but it does illustrate the need to think more deeply about exactly what we mean and what we're measuring or not measuring even when we talk about political discourse. So again, this is sort of very much work in progress, but I'm working towards building a more formalized model of sort of these three different layers and how to think about sort of checking your various discourse networks to see which of these layers you might be concerned about or need to investigate more. Okay, so then you may also want to know how we do this in code. So I will switch over to that. And I guess before I do that, I'm gonna pause. Any thoughts or questions on sort of the big picture here before we get into the coding side of things?
I received another question via direct message, and I think it referred to the end of your first application slide where you were talking about a specific tweet within the broader network. And the person asking the question wanted to know how that single tweet was selected out of the entire sample or corpus of tweets.
So I'm not sure exactly which slide that was.
I think it must have been
They
maybe
don't.
the,
Oh, go
not
ahead.
exactly sure, maybe the person asking the question could clarify.
Yes, so can I ask my question directly?
I think your audio is so the volume is very low. Maybe you can speak a little bit louder, please.
Yes, so am I audible now?
Still very quiet.
Oh, so I'm speaking quite louder from my side, but probably I'm not clearly audible. So should I write my question in the chat box?
Yes, I think that would be helpful.
Thank you. So, but anyway, it's like it is about the next slide wherein single tweet was selected out of the many tweets, and then a network was prepared, and the network prepared was entirely different from the original semantic network of the tweets.
Oh yeah, so I think the question is about this slide where I was comparing sort of the single tweet per conversation network to the all original tweets conversation. So the way I've done it here, and there are sort of certainly different ways you could do it, but so the image on the right is the full corpus, so it includes every single tweet. And then the one on the left, basically I iterate over the tweets, and for each tweet I see, I keep a record of the conversation ID for that tweet. And so then when I get a new tweet to look at to see whether to add it to this network or not, I first check the conversation ID. And if it's an ID we've already seen, then I basically just ignore that tweet and don't use its hashtags at all. Again, there are different ways you could do this. So you could sort of randomly select a tweet from each conversation, or you could just do it with the first tweet you see. The tweets aren't actually saved in any order, so doing the first tweet I see here is essentially random, which is part of why I've done it that way. But I do think that would also be a good, again, this is sort of a anecdotal example of why we might be concerned about this thing, but I think that would certainly be a robustness check you would want to do before sort of really taking any strong results from this kind of approach, is seeing, like, depending on how you choose that tweet from the conversation, does it influence exactly what you're seeing? So that's a great question. Thank you.
Thank you. Thank you very much for answering the question.
Okay, any other questions or comments? All right, I am going to switch my screen share here. So now I have to find the, okay. Now I have to move all my windows again, sorry. Let me get my chat open. Okay, so I see that Dennis has put the link to the materials in the Dropbox links in the chat, so definitely feel free to take a look at that. The main file, there's a .ipynb file. It's a Jupyter notebook, so that's the document that I'm looking at now. There's also some data files in there. I've included in this file sort of direct links to download those. And we'll be looking particularly today at these first two files of both the original tweets file and the conversation networks file. Oh, sorry, put it in Markdown there. So if you do want to run through this on your machine, you can download all of those and sort of just put them in the same folder somewhere. I was going to provide, if you don't have Python on your machine, you can also do some of this in Google Colab. But Google Colab is really annoying about loading data in a way that drives me crazy. So I ended up not using that. But if you do want to play around with that, that would be another option if you don't have Python set up on your computer. So a few things to note here. And again, I'll say, feel free to put things in the chat if you have any questions, or, if you want to unmute and ask, you're more than welcome to do so. So each of these files has sort of two file extensions here. So they're JSON.jzip files. So this gzip is basically a compression, so it's very similar to zip. I just use gzip because. And then JSON is the raw data format that the API, the Twitter API returns. So I partially wanted to show, like, working with JSON data here. JSON is the kind of thing where, like, I feel like when I first started working with it, I was like, what is going on? Why is this happening? This is a mess. But then once you get used to working with it, it's fantastic. I think also, in my experience, at least for our users, it's a little bit more challenging because it's explicitly not in sort of like a table or data frame format. But that's one of the things I at least like about working in Python, is that it sort of loads natively as what's called a dictionary in Python. So a Python dictionary comes from the fact that you sort of got this key value pair. So in a actual dictionary, you might have a word as a key, and then you look it up in your dictionary, and then you get a description or a definition of that word as your value. So that is sort of the idea behind a Python dictionary, which again is sort of the format that JSON takes. So here's just an example of one tweet. So we've got these curly brackets indicating that this is a dictionary we're looking at. The first thing here is a key. So we've got an ID key and then a sorry, I keep putting in markdown. The colon indicates, so this here is a key value pair, where the key is ID, and then this number, or it's a string here, but this value is the ID of the tweet itself. We also have keys for author ID and for conversation ID and text and other things. One thing to note is that unlike a list, these keys are not ordered, so you can call the value by looking at the key, but there's not like a specific order to these. So I rearranged them so that they would appear in a more conceptually friendly order here. But even one of the things that's annoying about working with the Twitter API is like the order. If I retrieve two tweets, the keys won't necessarily be in the same order, and then also some keys will just be missing. So like here, if we wanted to look at hashtags, which we'll do later, like this is under, you can have nested dictionaries. So we've got an entities key, which then has this hashtags key under it. And if a tweet doesn't have any hashtags, this will just be gone. So you can't even say like, show me the hashtags, because that will just throw an error because the hashtags key isn't even in the dictionary. And we'll see a bit more of that later. So that's just sort of the setup of what the data looks like and how we can sort of start thinking about and working with this data. So here's a whole bunch of packages that I'll be using here. So these first two, gzip and JSON, are just for loading the data itself. NetworkX will be using for the network analysis. This is a really great package, has a lot of different functionality to it, can be very helpful for doing network analysis in Python. This Iter Tools package is something that I'm just a fan of. It makes certain things easier, and I'll have a specific example of that below. It's very good at iterating through things. Has lots of tools for that. NumPy is basically a numbers thing for Python. I like to call it NumPy in my head, but NumPy. So it gives you lots of like math things that are just helpful. InfoMap is the specific algorithm we'll be using for community detection. And there's lots of information about how InfoMap works. I'm not going to go into detail on that today, but if folks have questions, I'm happy to chat about it more. And then Matplotlib does all the plotting, and then Seaborn, I just like the color palette, so I'll use Seaborn here. You don't actually necessarily need to use Seaborn, but that's what I'm going to do. Okay, so
a quick question here, Sarah.
Sure.
I'm not sure if anybody else had the same problem in case they were following along, but when running the 6th line on InfoMap, I get a module not found error.
Okay, so yeah, if you don't have a module installed, you'll need to install it. So you can do that either from your command line, or you can do that directly in Jupyter Notebook. Depending on how you have Python set up, I feel like this is not recommended because some people will be like, this will break your Python, don't do it. But people do it all the time. So you can, if you use this exclamation point, then you're telling the Jupyter Notebook that you're running a command line. So you can just use pip and say pip install InfoMap. And that should work. I think I already have it installed, but yeah. So here it's telling me that it's already satisfied. But if you run that just directly within your Jupyter Notebook, it should install it for you, and then you can rerun it. And that should work for any, if there's any other packages that aren't sort of already installed in your machine, you can do that. And then if you did want to do this from your command line, it's again just this thing, and then without the exclamation point, because the exclamation point here just tells the Jupyter Notebook that you're running something. that you're running a terminal command, essentially.
Cool, thank you.
Yeah, of course. Yeah, and if other folks have any other questions, feel free to jump in at any time. Okay, so here we'll start by loading. This is just a sample of the full data, so this you won't see the exact same results that I was showing in my slides here, but it's just a little easier to work with a slightly smaller sample. So we'll start by loading some of that data. And so again, this is in a .json.gzip file. I have it set up so that each line of the file is its own tweet. So we'll read the data in line by line and then use this JSON.loads to basically read that data, and it will read in as a dictionary. We'll also create an empty list and store each dictionary or each tweet in there. So our final thing will be a list of dictionaries where we'll call our list tweets very creatively, and then we'll have the square brackets just indicate that it's a list. So we'll have a list, and then each item in this list will be a dictionary. In Python, we can use len to figure out sort of how many elements are in that list. So it's basically length, but shorter. And I'll also note that Python uses zero indexing. These are the kinds of things that confuse me all the time when I try and switch between languages. So here we'll just initiate tweets as an empty list that we'll be using to store our tweets as we read them in. Here we can use gzip.open because it's a gzip file. This is basically using the gzip package to say, oh, we want to open it with this compression algorithm. So we'll open the file, we'll open it in read mode here, and then we'll call this fp. And this is just something like this sort of the standard syntax for how you open the file. There, you could also open it and then explicitly close it, but use it by using this with open statement. Essentially, you're saying like, while it's open, do stuff, and then it will close itself. And then we call it FP here because we do, it's a standard thing, but we could call it whatever we wanted. So then we want to iterate through each line here. So we've called our open file FP. We'll use this read lines to look at each line. And so one thing also in Python is that you can essentially name variables on the fly here. So like the convention is that you choose names that are explanatory. So here we're looking through a series of lines. So we'll call each thing that we're looking at a line, but we could say for item in fp.readline or for thing or whatever. We could basically are naming this variable in this loop. So we'll iterate through each line, and then for each line, we're going to decode it. This is partially because it's in a gzip file. We just need to, this by default, we'll decode it into UTF-8. If we wanted to decode it into something else, we could specify that here, but just the decode will work. And then we will use the JSON package to load this as a JSON object. And we will just call that JSON object tweet because we know it's a tweet. And then we will append this to our list. So tweets is the name of our list. We're appending the tweet line that we have just seen. And then at the very end, we will print out how many tweets we saw altogether. And this format here is just like fancy Python for printing variables within strings. So these curly brackets here are just saying, oh, there's going to be a variable here. And then I use .format, and it'll sort of plug in the value of len tweets within those curly brackets. So just looks nice that way. So then when we do that, we can also look at what type of object this is. So we know it's a list because we created it as a list, but this type function can be helpful for sort of making sure that things are what you think they are. Again, this list is 0 indexed. So tweets 0 is the initial item that's in this list. And as we would expect, the type of that initial item is a dictionary. In fact, all of the items are dictionaries, but just as an example, we can sort of look at a random tweet. Tweet 9 here is actually the example tweet that I showed before. You can look at some other tweets as well, which like some of them have more fields that show up or sort of other things going on. I chose like this one has a URL in it. I chose 9 in part because it's like a nice simple tweet that has all the key elements, but like nothing too crazy going on. Okay, so now we have a list of things that look essentially like this. And we want to build a hashtag co-occurrence network from that. So first of all, just thinking about how we might approach this. So there are 2 ways we could do it. We could see up here, there's this text field. So text is the key in this dictionary, and then it gives us the text of the tweet itself. So one thing is that we could just go through this text field and essentially search for this pound or hashtag symbol and then find any string that sort of follows that. Twitter actually makes it even easier for us, where it does have this entities hashtags thing. So we'll actually use that here. For other types of data or semantic networks, you may need to actually do like search the text itself to look for certain patterns, but here we'll just use this hashtag field directly. So I know it can be a little bit hard to see here, but sort of in this example, so we're looking at the 9th element in tweets here, and we've got the entities key, which then gives us this hashtags, entities gives us a dictionary where it has a hashtags key, hashtags key, and then that key gives us a list, and each item in that list is also a dictionary, and we want the tag key from that to give us the hashtags. So here we have, for each item, again, we're sort of naming this on the fly, we could call it whatever we wanted, but for each item in this tweet, where we're looking first in the entities key and then under the hashtags key, we want to print the tag for that item. So the item itself is going to be this dictionary, and then we want to call the tag from that dictionary. So this is the kind of thing also where you get very used to looking at these, and like often when I'm first writing code for things like this, I need to print out an example, and I literally go through and be like, okay, so the first key is the entities, and then the second key is the hashtags, and like you sort of print out different stages of it until you figure out like, okay, I've got the right nesting structure here. So that will give us sort of these 2 hashtags that we're interested in. Another thing that we can do in Python, if we want to be a little fancier or more Pythonic, partially it's also one of those things where you just get used to writing things in this way. You can also use what's called a list comprehension. So here we have a for loop, but a list comprehension will do the same thing essentially in one line. So here we're telling Python that we're going to make a list. We're basically just telling it by putting those square brackets around it. And the list is going to be item, it's going to be the tag element from item. And then this is the same, where it's for each item essentially in this nested structure. So that will just directly give you this list of things. And here is where we start to use Iter Tools, where like imagine that we go through a tweet and we get our list of hashtags. Let's say that it has 3 hashtags, and we want to now look at every pair of hashtags because we want to consider those pairs to be connected to each other. So we could do this in a for loop. So for example, if we have hashtags and those are just 1, 2, 3, we could do a nested for loop and it would iterate through each of these things. Now, one thing to notice here is that when we do that, we do get self loops. So we've got 1 and 1 are in both lists, we also get repeating edges. So this would be good if we were looking at a directed network where the edge 1, 2 is not the same as the edge 2, 1. But in this network in particular, anytime 2 hashtags co-occur, we just consider them to be linked to each other. So we actually only need to count that pair once, and 1, 2 would be the same as 2, 1. So we can do this just a bit more efficiently using, this is the Iter Tools package, which we imported by we called it IT when we imported it. So we use the combinations function from Iter Tools. And this essentially does the same thing, except it does it much more efficiently. So it just gives us the unique combinations, not including self loops or repeats. And if you, Iter Tools has other things as well. So you can also do like permutations with replacement. There's sort of lots of different things you can do if you need to iterate through things in various creative ways here. So that will just make it a little bit easier. So I'll talk about NetworkX in just a minute, but sort of the conceptual approach here is we look at each tweet, we find this list of hashtags from each tweet, and then we iterate over each pair of hashtags and say there's an edge every time there's a pair. So any questions so far? And I can also let me know if I'm like going too fast, too slow, any feedback like that, just let me know.
It's okay for explaining things in so much detail. I hope this time I should be audible.
So you were very loud at first with a lot of background noise, and then I feel like you're even more quiet now.
All right, thank you.
But if you have a question, maybe if you want to put it in the chat, and I'm happy to answer it. Okay, so then now just to give a brief introduction to NetworkX. So earlier we did, when we imported all of our packages, we imported NetworkX and we called it NX. Also note, so this is another Python thing where like we could just import NetworkX and then anytime we use a function from NetworkX, we call it NetworkX. But Python tends to have, packages have like a 2-letter or sometimes 3-letter standard for how you name it when you import it. So this is basically making a shortcut so that instead of typing NetworkX every time, we can just type NX. We could call it something else if we wanted to, but then it would annoy other people who are trying to look at our code, because again, these things are sort of standardized. Although I will also say there's sometimes like I'm using a new package and I have to Google like, what's the conventional thing to call this new package if I am not used to importing it. So it's just one of those things you have to learn. Okay, so NetworkX is a great package for doing network analysis. I think I included a link to the full documentation there. This is actually not the link that I meant, but you can look it up. It's pretty easy to find the full documentation. You can create directed networks, you can create undirected networks. So here we'll just use graph with a capital G to indicate that we're making an undirected network, and this is just initializing it as an empty network. And before we sort of look at this through hashtags, I'll just go through some brief examples of how you can use this. So now G is the name of our network. We can add nodes to our network. So basically now if we say print g.nodes, it gives us a list of all of the nodes. We can also add edges. So we'll add an edge between nodes B and C, and you'll note that this automatically adds, when you add that edge, it automatically adds those nodes to the network if they weren't already in the network. And then you can also print the edges and see that it sort of appears as an edge. You can also add weights or other characteristics to things. So here we'll add an edge between nodes A and C, and we'll give it a weight of 1. And then to access those attributes, then you can say, you have to say data equals true. So here G.edges is the same that we used before, and that will just print this list of edges. But if we do the same thing and put data equals true here, then it will tell us the weight of those edges. And you'll see here that when we added the edge AC, we did specify the weight. So it is there with a weight of 1, and this is a dictionary. And again, we could add other attributes to this. We could call them whatever we wanted. And then for this edge BC, we did not add a weight to that. So it has sort of an empty dictionary associated with it, but we haven't specified a weight for that edge. So because this is a dictionary for edges where the weight is specified, we can access that using basically the attribute or the key, the attribute name as the key. So again, this is an undirected network. So whether we say it's edge AC or edge CA, we're going to get the same weight because it's the same edge. And again, for this edge BC, it just has an empty dictionary associated with it. So if we try to sort of access the weight attribute, we'll get a key error because that key does not exist in this empty dictionary. So one thing that we can do, which we will see a little bit later, is that we can use the dictionary method called setDefault to ensure that an attribute is added to that dictionary. So here, I'm just going to iterate over all of the edges in this network. So here again, we're sort of naming this on the fly, and Python does this thing where, so let me actually show this in a separate cell. But like we could say for item in, so it's because I have the whole network in there, but this is why you should reset your kernel before you show examples of things so that your data is in the same place that everybody else is. But anyway, you get the idea that it's essentially each of these edges is a tuple that has 2 different nodes in it. So here we tell, like Python knows that it's getting this thing that has 2 elements in it. So we're just telling Python, oh, the first element, call that one I, the second element, call it J. And Python sort of just knows automatically that that's what you're telling it to do. So we'll iterate through those edges. And then for basically this edge between the element I and the element J, we'll set the default to 0. And then we can add a weight if we want to do that. We could also, I don't know, subtract weight or do whatever we wanted. But by doing this, it will allow us, it will basically add this weight item to the dictionary, and it will set it to a default of 0. So that would sort of get around this issue up here where when we used the weight parameter, it threw an error because it wasn't in the dictionary. But by using setDefault, we're like, just add this as a key to the dictionary, and here's the default value you should give it. I'll also note, so you could add node or edge attributes that could be anything. So like weight is a common one that is used, but there might be other things in your network that you might be interested in. For here, we'll keep track of like the count of how many times different hashtags occurred, things like that. But you could also be like, the weather is sunny, or like this can be very helpful in social networks, for example, where you might need to say like, oh, this person has this title or this rank or something, or there's just other metadata about either the nodes or the edges that you want to be keeping track of. So we won't see too much of that today, but I just wanted to note that. Okay, so now we have all the pieces to be able to make this hashtag co-occurrence network. So we're going to see this like long chunk of code. But it's a lot of stuff that we've already seen. So again, we just start by initializing our empty undirected network. Tweets is the name of our list of dictionaries that has all our tweets in it. Here we'll name those elements on the fly. So we're just going to call them for tweet in each tweet. For tweet in tweet. So for each tweet that we see in our list, again, these tweets might not have a hashtag, so we'll use this try except language. So we'll try finding a hashtag, and then if we don't find a hashtag, we'll just say hashtags is an empty list. So then to try and find a hashtag, this tag details will again give us that dictionary, and then we use this this list comprehension to say our list of hashtags is the tag element in those dictionaries. And then if this gives an error, essentially it would be a key error. If there aren't any hashtags, then we'll just call that an empty list. Now, if we only have one hashtag, then we have a node but no edge. So hashtags here is a list, so we just want to call this, our hashtag will be the 0th element of that list, and then we'll just have a string instead of a list. We'll add this as a node to our network. Just for fun, we'll keep count of how many times different hashtags occurred. So we'll use this set default parameter to create a new attribute that we'll call count. We'll set its default to 0. And then because we have just seen H1, we will increment this by 1. But then we don't need to add any edges because we only have a single hashtag. So this is else if, essentially elif, the length of our list hashtags is greater than 1. So you'll note here, if there aren't any hashtags, this is 0. So essentially nothing ever happens to that, because if it's equal to 1, something happens. And then if it's greater to 1, something happens. So now we'll use that the combinations package, or the combinations function from Iter Tools, where we're saying from this list hashtags, give us all combinations of length 2, and we'll call those things H1 and H2. Again, sort of arbitrarily naming these hashtag 1, hashtag 2. So the first thing we'll do is we will add this edge. If this edge already exists, then sort of nothing happens here, essentially. So we're not overwriting any data by adding this edge, but if it doesn't exist, then it will add that edge. And if these hashtags don't exist as nodes, it will add those as nodes. Again, we use this set default parameter or function to create a weight attribute. Again, if it does not already exist, it will be added to the dictionary with a default of 0, and then we'll increment that by 1. And again, because it's an undirected network, doing it this way sort of gets both H1 connected to H2 and H2 connected to H1. And again, just because we're counting how many times each of these hashtags occur, for each of the hashtags that we'll see, we'll make sure that this count attribute is in its dictionary, and then increment that. So if we run that whole code, then it will tell us sort of the number of hashtags. The length of G gives us the number of nodes in this network. So here, again, it's just a sample of the data that I was showing before. So about over 100,000 nodes in this network, where each of those nodes are hashtags. So now that we have a network, there's a number of things that we could do. We could look at the degree distribution. So g.degree gives the degree distribution by saying what the weight attribute is. I'm saying that I would say that I want a weighted degree distribution. It by default returns a dictionary view object, or I don't know, it returns something weird that I don't like. So I coerce it to a dictionary because it's essentially in a dictionary format, just makes it a little easier to work with. So as you may know, many networks have a heavy-tailed degree distribution. So if we look at this in a sort of standard histogram, so this is the degree of a node or a hashtag, and then this is how many times we see that degree. It's not very helpful because we have a lot of nodes that have a low degree, and then out here we can't even see how many there are, but there are some number of nodes that have a very high degree. Okay, so this is not very helpful, but I like to show it anyway. So one way, if we want to look at this degree distribution, would be to look at basically log bin the data and to look at it on a log plot. So to do that, basically, we want to take our x-axis here and cut it into some number of bins, we'll call it MB bins, where each of those bins are of equal size in log space.
Sarah,
and
sorry to
then,
interrupt. There's another question that I received
Sure.
via DM. And it's about whether edges will get created among all pairs of vertices or only in between those nodes, so hashtags, which actually appear within the same tweet.
Yeah, so the way we've set it up here, and this is fairly standard for hashtag co-occurrence, where so this loop is over, like in all of this code is for a single tweet. So for that tweet, we're looking at what hashtags are in that tweet and then adding edges between all the hashtags in a tweet. So if tweet 1 has hashtags 1 and 2, there will be an edge between that. If tweet 2 has hashtags 2, 3, there'll be an edge between that. But then 1 and 3 will not have an edge because those hashtags were in different tweets. Yeah, so that's how it's set up here. So then I have this fancy function. It's not that fancy, but for log binning, where again, we're taking a vector of data. We're going to cut it into, here by default, 50 bins, which we'll cut it, but we'll tell it by default that we want this to do it in log space as well. We don't have to do it in log space. So we'll cut it into 50 bins that are equally spaced in log space. And then we'll calculate the density of, in this case, the density of nodes that have that degree that sort of fall within that bin. And we don't necessarily need to go through this function in detail, I think, but this is one of those code snippets that I like go back to all of the time when I'm making degree distributions for networks. So it's basically like you define your upper bound, your lower bound. We convert it to log space. And this is all using the NumPy package. We create, here we've told it 50 by default. So we split it into 50 equal sized bins that are equal sized in log space. Using this diff function basically helps us compute the midpoint of each bin, so that will actually be sort of what appears on the x-axis. And then we create a histogram. And if people want to know the details of this, I'm happy to talk through it, but it's mostly it's just like math, I don't know. So it's then creating the histogram, and here we'll make it, convert basically the density as here instead. So when we do that, it gives us a much more useful plot where we can actually see, okay, so for degree 1, we have a high density there, and then we have some nodes that have degree like 10 to the 5th, and there's not very many of them. It's a pretty low density, but we can see that there. So you may, when looking at degree distribution, see a lot of plots that look like this that are essentially log binned. And I know we're running close to the end of our time here. So again, feel free to interrupt if there are other questions or things you want to make sure I get to at the end. Otherwise, I'll just sort of keep going through at least the first portion of this. So if we want to look at the top hashtags here, those would be the hashtags that have the highest degree. I'm also going to use this enumerate function, which essentially just like counts things. So if we had just said for item in A, where I think I deleted the thing that defines A. Just make A a list. And then basically you're just counting the things in that list. So again, I think I mentioned that things in the dictionary are stored in arbitrary order. So if we just look at sort of the first 5 things in our dictionary, they can be basically anything. We can also sort our dictionary. So we'll sort it based off the second item in the dictionary because it's 0 index. So the key is item 0, the value is item 1. By using reverse equals true, we'll sort it from largest to smallest. And so then that basically makes a sorted degree thing where if we use enumerate and look at just the first 10 elements here, we get sort of the nodes with the largest degree. So one thing you'll note here is that we haven't done any processing of this text. So we've got things like Black Lives Matter here, and then all lowercase Black Lives Matter there, capital versus uncapital BLM. So this is something where you probably want to do some pre-processing. One thing that I'll show briefly here is just how to make it lowercase. But there's also, I think, sort of larger questions about what, it's if there's a misspelling of a word or something in a hashtag, do you want to consider that the same hashtag or a different hashtag? And so there's certainly some manual things that may need to be done when thinking about hashtag co-occurrence. But just certainly as the top level, we can use this item.lower or just .lower, we'll make it lowercase. So we're basically going to create the network all over again. Here I've just wrapped it in a function. So we're going to, I've called my function get network. I'm going to give it an empty network and then a list of things a list of tweets to look at. And then here I've just made a few small changes. So here when I get my hashtag list, I use this lower case to lower, make every hashtag, make all the characters lowercase. And then because this could potentially result in self loop. So if there's a tweet that has hashtag capital BLM and hashtag lowercase BLM, I'm just going to, I'll coerce this to what's called a set, which then basically removes any duplicates and then put it back in a list because I want it to be a list here. So that will just remove any duplicates, but keep it as a list format. And then the rest of this code is the same. So again, if there's only one hashtag, we just add the node. And then if there are, I should have changed this. So again, this is because if the list is empty, it'll have length 0. So if I didn't say this and just left it as else, then empty, it would get empty hashtag lists here as well. I think actually in this data set, it turns out that they all have hashtags, so that's why it didn't matter. But in principle, we should do this. And then, so if there's if there's 2 or more hashtags, then we'll add that edge. And then that is the end of the function. So here to call the function, we'll again just initialize our empty network and we'll pass it our network G and our list of tweets. So here I've just copied the number of nodes that we had in the original network where things were not lowercase. And so here we see we get slightly fewer things now that we're sort of making everything be lowercase. So we can do the same thing where we look at the top degrees again. Here, again, we'll sort our dictionary using the values, which is the degrees of the dictionary. And so we look at the first 10 items in the sorted dictionary, and we can see sort of the most popular tweets or the most popular hashtags that were most commonly used or have the highest degree here. So as I mentioned, there's sort of no ideal way to deduplicate or disambiguate between these things, but it's a larger conversation. So then if we want to visualize this network, I again have a function for doing this, and this is a more complex function than you necessarily need, but this is if you want to make it kind of pretty. If we just wanted to plot the network, basically the lines for doing that is here where we are calculating, we're using a spring layout to calculate the position of each node. And then we're drawing those nodes and we're drawing those edges. You don't necessarily, with NetworkX, you can either draw things independently or you can sort of just say draw spring layout. Usually that ends up with your plot just looking really bad. So that's part of why I have it broken up here. But this function does a few different things. So it will filter the network for the purposes of visualization, identify communities in that network, and then sort of draw it in a few different, or like plot it out. I'll now scroll down here quickly just to show. So like, here's where I call the function, and this is the output of the function. So this is the full network with sort of this original corpus of tweets. So I'm giving it G. So this is that network that I just constructed, the hashtag co-occurrence network, and I'm going to tell it to label some of the tweets. And now I'll scroll back up and go through this function. So G is the name of my full network. I've set label to true, and by default, I'm thresholding at 500, in part because some of these edge weights are very heavy. So this just sort of, in terms of visualizing the edge weights, makes it a little bit easier to look at. So the first thing I'll do is I'll look for connected components in this network G. And I will print out the number of connected components found. And I'm sorry, I'm going to just keep scrolling. So here, this original network had like 7,000 connected components. So some of these hashtags were just isolates, for example, where they appeared in a tweet, but not with any other hashtags. So the first thing we want to do is look at the largest connected component here. So this is a list of all of our connected components. We'll get the nodes from the largest connected component and make a subgraph based off of that. So now we have GC, which is a subset of our full graph C, where we're saying it's basically just the largest connected component. And so here, just for the record, also we print out the number of hashtags in that largest component. So if that component is greater than 100, and this is a function that I was writing to use for other visualizations as well. So if for some reason, like our largest one, our largest network is actually incredibly small, then we'll do something else. But assuming that we have more than 100 hashtags still in this largest connected component, then we'll start by identifying the top nodes in this connected component. So we'll again get the degree list, but here we're just getting the degrees of this largest connected component. We'll sort those degrees again so that the largest degrees are at the beginning, and then we'll just get a list of the top 1,000 hashtags in this network. So this will give us those nodes with the highest degrees, and then we'll make another subgraph where here we're taking a subgraph of this largest connected component, but with just these top hashtags. And so now our network is called sub, and we'll print out how many top hashtags that we're getting. Here is where we'll then sort of thin and threshold the weight. So because we don't want to accidentally like do anything to our original network G, we'll first create an empty graph that we'll just call H for fun. And we'll go through every edge. So I and J will be the nodes here. And then details, because we've set data equals true, details will be a dictionary with those edge attributes. So here, details will have a weight attribute telling you the weight of that edge. And so we'll just divide the weight by our threshold, which by default, as part of the function, we put it at 5,000. And so This basically serves two purposes. One, when we visualize the network, we'll show the edge weight. So we could do it just later as part of the visualization. We'll like sort of scale that there, but it also will say if we'll only actually add this edge to our network H if the weight is greater than 1. So this is just sort of an arbitrary decision for the purposes of visualization, of saying like, oh, if the weight isn't actually that strong between these two edges, then we're not going to visualize it. And this can also help with like avoiding hairball kind of visualizations. So then just, again, so we know what we're doing, we'll print out how many nodes were retained after this edge thresholding. The final thing we'll do, almost final thing we'll do, is calculate the K-core with K equals 5. So here the K-core is basically like you're cutting off everything so that the minimum degree in the remaining network is 5. So again, this is for visualization purposes to help look at sort of the core elements of this network. And we had put an if statement up here. So if we only have 100 nodes in our largest component, then we'll just ignore all of that and just keep all of those nodes. So then we start to get into the visualization part. I know this is a lot of pieces, but I feel like I was hoping it would be helpful to sort of go through sort of the complicated version of this code, just so you can see sort of how it works under the hood, at least when I'm sort of making some of these visualizations. So just as a check, we should only have one connected component at this point, because we had looked at connected components before, but we'll just double check that. So again, we'll get the number of connected components we have and just print that out. If we need to, we'll again just keep the largest connected component. If we still only have one connected component at this point, then we're fine. Then we'll use the info map algorithm to identify communities, which is basically done by doing this. So core at this point is the name of the network that we're actually looking at for visualization purposes. And then we'll run the info map algorithm. So this algorithm basically works by doing a random walk on the network and identifying sort of neighborhoods that it gets stuck in, as sort of the high level idea. So then it will return a, basically for each node, it will return a community label for that. So we'll make this a dictionary where it has, for each node is the key, and then it will say a label, a community label, which will be like 0, 1, 2, 3 or whatever. And then we'll see how many communities we found here. And then we can plot this. So again, core is the name of the network that we'll actually be visualizing here. We'll tell NetworkX that we want to use a spring layout. You can sort of set the random seed just to make sure you get the same results each time. And we want to have this be a weighted spring layout. So we'll use the attribute weight when calculating the spring layout. To visualize the nodes, we'll first calculate the degree of this network core that we're visualizing. And then we'll calculate node size, as we'll just make it 2 times the degree size. Again, this is just sort of like, I tried around with different things and this seemed to look good. So this is sort of for visualization purposes. We'll color code our communities. So each community label is going to be an integer. So we can make a list of colors and sort of map that to our nodes based off community. And then we'll tell NetworkX to draw this. And then we'll do a similar thing with edge weights, where we sort of iterate over these edges and keep a count of the weight of each, and we'll draw the edges using this edge width, which again has been thinned as before. If we are labeling things, so these are just a list of, when I had been going through this and looking at some of these communities, these were some of the key hashtags that seem to be showing up in the community. So I just have a list of sort of key hashtags to label here. And so I'll also here essentially create a dictionary where by default, the label for each dictionary is just an empty string. So it essentially has no label. And then for these ones that I'm keeping, I'll actually add that in. So by doing this, we can sort of label the specific hashtags that correspond to any of these strings. So then the last thing we'll do is we'll draw our labels and then we'll tell it to plot. So again, here's the output from that algorithm. So you can see sort of the various trimming steps that it took. It ended up finding 6 communities, and then it labeled those specific hashtags that I had mentioned. If any of those hashtags do not appear in this network, then they're just ignored in terms of the label. So I do know that we're just about at time, so I'll go ahead and stop there. But if anyone has any questions or comments, I know that was sort of a lot that I just powered through, but I'm happy to chat further. And also you're always welcome to reach out if you have any additional questions for me.
Perfect. Thank you so much, Sarah. So we have a couple of minutes. We can also go briefly over time if that's okay with everyone for questions and comments from the audience. Anyone?
For this wonderful talk, I hope this time, am I audible now?
I think we still have problems hearing your audio. So if you could type the question in the chat, that would probably be better.
Hi, can you hear me? I'm Dilrukshi.
Yes, perfect. Thank you.
Cool. Okay. Just wondering, this could not be a direct question, but comments also welcome. So I just want to know if I'm sort of using Gephi for all of these network diagramming things. Do you see something, that you can do in Gephi that you could do in this Python frameworks?
Yeah, that is a great question. So one thing that I prefer about Python over Gephi is that I feel like I have more control over specific things. So for example, if I wanted to do community detection in Gephi, it does have that built in. It uses a version of the Louvain algorithm. But then if you want to use, like if you wanted to use InfoMap in Gephi, then basically you can't. So for me, I feel like Python gives me a little bit more control over like exactly what I'm doing and makes me more aware of like the specific choices and implications of those choices and like the exact code underlying any of these algorithms. But that being said, one thing that I will often do is like, I might use Python for analysis. So for example, if I were doing something with community detection where I really wanted to know like how robust are these communities, which nodes are like really community in these communities versus what nodes might be on the edge of communities. So then you could run like a bunch of different community detection algorithms or do a few things to sort of see how these communities change depending on choices. But then I would actually, like for a final paper, would do the visualization in Gephi because then you get the nice visualization. So I've certainly done that as well, where sort of the analysis piece is primarily in Python, but then the actual visualization. And I would sort of do the filtering and stuff in Python and then output sort of whatever core nodes I wanted to visualize in Gephi. I do think that Gephi is fantastic and it definitely makes great visualizations. And I guess, again, my only concern about Gephi in terms of scientific research is that sometimes it's, I don't necessarily feel like I know exactly what is going on under the hood, which can be fine if it's just for the purposes of visualization. But if you're really trying to infer something from that, I feel like it can be helpful to know exactly what's happening. But great question. Thank you.
Thank you very much.
Okay, I've just received Rinkaj's question via the chat. So first of all, he thanks you for the great talk. And he wants to know whether it's okay to model things as a link prediction problem especially constructing semantic networks from conversation networks. And I'll also throw in another question that I just received from, can't see the name, Manuel. Can you think of any application of these networks that you taught us how to construct today outside the world of Twitter?
Yeah, those are both great questions. So on the first one, sorry, I have such a short-term memory. Can you repeat the first question again?
No problem. The first question was, is it okay to model things as a link prediction problem, especially constructing semantic networks from conversation networks?
Yeah, I think that's definitely okay. I find that like questions of prediction, it often depends on like the specific field and the specific type of research you're doing. So for example, in work that I've done looking at recommender systems, I'll often approach that as sort of a link prediction type of problem where I'm interested to see like, will this person respond to that person? Will this person be engaged in that conversation? So sort of approaching it from a prediction framework. Whereas for other things like, this is a conversation that has already happened, and I'm more anecdotally interested in sort of what existed in a non-predictive way. But I think they're sort of both useful ways of approaching these kinds of questions and thinking about them. So then for the second question, yes, definitely applications beyond Twitter. I think for me, particularly since the pandemic, I feel like I've just been living in Twitter land. Everything is Twitter these days. But I do think that certainly other social media platforms, which have the benefit of sort of having all of this trace data or sort of a recording of these conversations. But I also do think that these kinds of applications and approaches could be used in other types of conversations as well. So that's one of the things I'm interested in doing with this work and thinking about for, in developing this as a more robust framework, is thinking about like, okay, so if I were actually looking at, transcripts of a face-to-face conversation, what would that mean, and thinking about these different levels of things. And I don't necessarily have an answer to that question, but I think it's a really good question to be asking.
Cool, thank you. Do we have any more questions from the audience? Okay, in this case, I'll quickly throw in two questions of my own, sure. Which are a bit about embedding the applications that you illustrated here today in a broader context. The first question is, what do you think, and it's one of the favorite questions that I ask when people present cool new techie methods, what do you think are the biggest research potentials with respect to potential applications? And I'm especially thinking, in political or the social sciences more broadly, about connecting network data based on tweets, which I think is an excellent, an application for this method, to connecting this with external data. So, I mean, if we're studying legislators, I think we could easily, connect this to characteristics of the districts in which they compete. We could also use other estimates based on Twitter data, so ideology estimates based on scaling models based on the textual contents of tweets, or use Pablo Barbera's method for modeling ideology as a function of joint following decisions. So I was wondering, if people want to get into this, what do you think is a promising arena for possible problems that they might want to look into? And then okay,
sorry.
No, answer that question first.
Yeah, because I won't remember afterwards. But I will answer your second question after I answer this one. Yeah, so I think certainly linking with external data is a really exciting area. So there is the work that you're talking about linking to legislatures. There's also an increasing amount of work where it's survey data linked to Twitter data. So like you'll have survey respondents volunteer their Twitter handle and agree to share their Twitter data. And that, again, sort of getting to questions of public opinion, you can sort of see people's survey responses to questions and also see what they were tweeting about. I also work with a data set where Twitter users are matched to US voting records. So we have some information about sort of the demographics of those users, as well as sort of their what party they vote for and things like that. So I think there's a lot of really interesting and exciting work along those lines. The other thing, I am particularly interested in thinking about sort of individual conversation health, but more broadly thinking about like the discursive health of the public sphere. So, I think there's a lot of very good concern that political dialogue is not in the healthiest place right now, and that there's a lot of room to improve what political dialogue looks like, both in terms of reducing misinformation, reducing hate speech, reducing even just toxic speech that's maybe doesn't quite rise to the level of hate, but is still not pleasant to be around. I think there's a lot of interesting questions like that, both in terms of sort of individual conversations, but then also more broadly, like what the public sphere looks like. So one of the things I'm really interested in here is thinking about like, are there certain things that, if a conversation is sort of going off the rails, is there a way to sort of bring that conversation back? Or what types of things cause people to exit conversations? Or like, if a conversation is becoming particularly toxic, are people going to exit that conversation, or are they just going to like double down and be more toxic in the conversation? And thinking about some of those dynamics, and hopefully then also thinking about some of the ways to improve those dynamics. But great question. And sorry, you had another question as well.
Yes, thank you. The other question, probably a very general question when people are working with tweets, and that's the question of replicability and reproducibility. Because as far as I'm aware, you can never share the full corpus of tweets that your analysis is based on. You can, of course, share the tweet IDs, but some of these may be deleted in the process. So essentially, you have a replicable pipeline, but an initial data collection effort that is never guaranteed to be reproducible. So what do you think are best practices, and how would you solve this problem?
Yeah, that is a really great question. And I think it's particularly important for like, in some ways, like the more salient a topic is, the more important that is. So I know people who are studying like tweets around the January 6th insurrection in the US. And many of those tweets have been rightfully deleted by Twitter. And so then that, like, it literally is impossible to recollect that data set. So, I do think there's the challenge here is also about balancing replicability with privacy and ethics, which are also really important. So I do think that sharing tweet IDs is essential and should always be done. But I also think that it's usually not appropriate to share full tweets or full corpus of tweets. But I do think that there are certain ways in which that can be done. So like, one of the things I've thought about here is if there's a way to have like sort of informal partnerships. So it's like, you can't necessarily make that tweet data public, but you can share it with other researchers under certain conditions. So you can imagine, some sort of peer review type of system where other scholars do get access to the raw data in order to be able to sort of replicate results, but not in a way that sort of greatly adds to the privacy concerns of sharing that data. Obviously, sort of setting up an infrastructure like that is a whole undertaking. So I don't know how close we are to doing that. But I do think that there are some sort of informal networks of people who can sort of do that work for each other in a way. And I think that's something that I would like to see expanded as well.
Right. Thank you so much for answering our questions and for taking the time to educate us about networks for political conversation. Thanks everybody in the audience for being here today and for participating and asking your questions. And yeah, let's all give a hand to Sarah. That was been really great. And we hope to see all of you next time. Bye-bye.
Thank you so much for having me. It's good to see everyone. Take care.